So first I would like to thank the organizers for giving me the opportunity to speak here. So this work is done in collaboration with Karel Netochny from Prague and Christian Myers from KU Leuven, where I worked as a postdoc. So I'll be talking about statistical forces from non-equilibrium medium. So first I will just define what do I mean by statistical forces, and then I'll discuss what happens in equilibrium, and then I go over to non-equilibrium case, and I'll discuss some applications of it. So let us think of a system where you have some macroscopic degree of freedom coupled to some microscopic degrees. So typically these microscopic degrees are fast and they relax much faster than the macroscopic one. And by statistical force, I mean the average force on one of these macroscopic degree, which is exerted when we average over the fast degrees of freedom. So I'll define it more precisely very soon. But there are several examples of such forces. So for example, pressure exerted by gas molecules on a piston. So the gas molecules are equilibrated or stationary, whereas the position of the piston would be the macroscopic degree here, and which is much slower. Also osmotic pressure on a membrane or Casimir forces, critical Casimir forces, these are examples of statistical force. So in equilibrium, these forces can be actually obtained from a potential, which is essentially the equilibrium free energy, and we want to see what happens in non-equilibrium. So there have been many works in this direction recently. So for example, people have calculated Casimir-like forces from non-equilibrium medium, also pressure and equation of state in active media, osmotic pressure from active solutes, and many other similar works. So the setup I'll be using, let me describe it in detail. So we have an equilibrium bath at some temperature T, so which is like the basic system, and then we have a non-equilibrium system. So that I will call medium eta, which we drive with some external drive epsilon, which can be electric field or some other fields. So this medium eta is driven, and then there is a probe, which is the macroscopic degree, which is a slow degree of freedom. That is coupled to this non-equilibrium medium. The probe can also be coupled to the equilibrium bath outside or not. I mean, it's not essential. So this coupling, we take some energetic coupling. So this U x eta is a joint energy, but we assume that the probe is much slower, so there is a time scale separation. So for example, one can think of a particle system. So these blue particles are fast heat bath, which gives the temperature T. And then these green particles are my medium, which is the non-equilibrium one, which is driven by some external field. And then there is a big particle like a colloidal suspension, which is the probe. And typically we would be looking at the position of the probe and what is the force exerted on the probe by these green particles, under the assumption that there is a huge time scale separation between the green particles and this disk. And of course, we always assume that there is an infinite time scale separation between the blue particles, which are the bath degrees. And so is it clear the setup? So blue particles constitute of they are just equilibrium bath, and then these green particles are the non-equilibrium kind of bath. So to define this non-equilibrium, I need the blue particles, because they are so these green particles have some local detail balance with respect to this thermal bath. So it's a 3-level setup. We have an equilibrium bath which gives me some ambient temperature, and then a non-equilibrium bath which gives which is driven characterized by some field epsilon, and then we have this probe which we will be looking at, and we want to measure the force on this probe. Yes. The blue ones are the fastest ones, so they are just equilibrium bath. I mean, you don't even need to think of blue particles anymore. You just need to think that there is a temperature, ambient temperature somewhere, and the green ones are much faster compared to this disk. So basically, we will always be talking about the green ones and this disk, and we know that there is a background temperature T. So with respect to this temperature T, there is a local detail balance for these green particles. So yeah, so now we define what I mean by statistical force more precisely. So we are assuming that there is an infinite time scale separation also between the probe and the medium, the non-equilibrium medium. So from now onwards, I will never talk about the equilibrium medium. By medium, I will always mean these green particles. So for a given position of the probe, under this assumption of infinite time scale separation, the eta degrees of freedom relaxes instantly to some distribution rho x, so which is not the Gibbs distribution because they are driven. And we calculate the force on the probe from this joint energy u x eta, and then we average over these eta degrees of freedom. So that is my definition of statistical force on the probe for a given position x. So is it clear what exactly I mean by the statistical force? So you can, so you can get pressure from this definition when when you consider the probe as a wall and you take derivative with respect to volume, and so for other cases you can get other forces, but typically here we are considering the position of a colloidal suspension, let us say. So in general, for non-equilibrium, this force has two components, one coming from equilibrium. So when this rho x is basically Gibbs distribution, and then when we drive this medium out of equilibrium, there is a correction which I will call Gx. So these are the notations I will be using. So Gx is the main quantity that we are interested in, and but before going to Gx, let us see what happens if the green particles are also in equilibrium. So but before that, what kind of questions are we going to ask? So we'll be asking what is the work that we need to do to move the probe by a small amount dx, and what happens when the medium eta is also in equilibrium, and what happens when it is driven out of equilibrium but close to equilibrium still, and what happens when it is further away from equilibrium. And I mean, since this is a mechanical force, it can be measured. So can we get any information about the non-equilibrium medium from measuring that work or that force? So these are the questions that we will be interested in. So let us first consider when the eta medium is also in equilibrium. So then for any given position of the probe, the distribution is just the Gibbs distribution, and then very easily you can see that this F equilibrium on the probe is just derived from a potential which is the free energy of this eta medium for any given position x. So we are always assuming that the probe is not moving when the eta is relaxing. So it's for a given constant x. So when we think of the joint system, so the probe and the medium, and then we see that the force on the probe is basically gradient, and typically it would relax to a joint equilibrium, and that relaxation is just a gradient flow, and free energy acts as the mechanical potential. So this thermodynamic potential is just converted to a mechanical potential for the position of the probe. So now we go over to the non-equilibrium case, and what we will see is that generically this gradient nature is not valid for non-equilibrium. So the statistical force would be a non-gradient force in general, and to linear order around equilibrium. So when this eta medium is close to equilibrium, this work done by the stat force on the probe would be related to the excess work done on the medium by this drive. So we will see it in details later, and we will also see that these forces provide information about kinetic aspects of the medium which are typically not picked up by equilibrium measurements, and they are also non-additive when we consider more than one media. So so first let us look at a very simple exactly solvable toy model to understand what we have been talking about. So we consider probes which are confined on a circle. So these are my probes, they are non-interacting, so we can think of only one probe, and that's coupled to some non-equilibrium degree of freedom. So for simplicity, we just take a 3-state process. It's the simplest one where we can drive the system. So we can think of it as an internal degree of freedom for this probe, and it's a 3-state process. So I consider this eta as discrete variables -1, 0 and 1. The numbers are not important, it's just a 3-state process. And we consider the probe is just a diffusing particle on the circle. So it's diffusing under this potential u x eta, some joint potential, and there's the noise. So this noise is coming from the basic equilibrium bath, the blue particles. And this eta is a medium degree of freedom, and we consider some joint potential u x eta. The form again is not important, it consists of sin x and cos x because we are considering the particle is on a circle. And then we have jump rates for this discrete process, which is driven out of equilibrium with this field epsilon, and which is also given by this energetic coupling and some prefactors phi. So, these prefactors are typically the time symmetric factors. We will come back to it later, but what we have here is a single probe which is large, which is macroscopic, very slow, coupled to some internal degree of freedom, which is a discrete process, which is fast. So, this discrete process relaxes very fast and the probe does not have any time to move within that time scale. And we want to measure the force on this probe coming from this internal degree of freedom. So, when this three-state process is given a drive, so this is a rotation in some space, we want to see what happens to the probe on this circle. So, is the question clear what we so it's basically arbitrary, but so it has to be a function of sine and cos because the probe is on a circle. We want it to be a potential, and then this typical form actually avoids special symmetries. So, if I take just eta minus eta, I mean without this eta square, we will see that the rotational component becomes 0 accidentally. So, it is just to avoid. Yes. So, this is a prefactor which is not picked up in equilibrium. So, you can it is like an Arrhenius prefactor, and this is the drive, it is the local detail balance. So, S is beta epsilon. So, this is the epsilon is the drive, and it is of this form because of the local detail balance, generalized detail balance. Yes. So, when epsilon equal to 0 irrespective of this phi, we will get a distribution which is the Gibbs distribution for eta. It would be just exponential minus beta u x eta. Now, we want to see what happens when epsilon is not equal to 0. So, typically we can also put some epsilon dependence on this prefactor, but I mean we will come back to it later. So, these are the plots for the equilibrium force and the correction to the equilibrium force. So, this was my potential, the joint energy, and then the force on the probe is just given by eta average and eta square average, which is just for a fixed x, you can calculate it very easily, it is just a three-state process. So, this is a very simple toy model just to illustrate the effects that we want to see. So, first we see that this green curve, which is the equilibrium force, it is antisymmetric about pi, which means if we integrate this we get 0, which is supposed to happen for a gradient force. Now, if we look at the blue curve, this is clearly not gradient. So, we measure the rotational component by integrating this over the circle, and this is the rotational component as a function of the drive. So, we see that the force on the probe becomes more and more non-gradient as we go further away from equilibrium, and basically the probe starts to rotate on the circle when we drive the internal degree of freedom. So, even though there is no direct drive on the probe, we see that it starts to feel the non-equilibrium in this medium. So, that is the first result, that you can see different I mean non-gradient nature of force on the probe when you drive the medium out of equilibrium. So, this was an exact calculation for this very simple system. Now, we go over to more general setup. So, for any general drive epsilon, we write the stationary distribution of the medium eta for a given position x as a perturbative series in equilibrium. So, this H is basically a perturbation series in epsilon. And one can show easily that the correction to the force is given by this form. So, it only depends on Hx, and work done to move the probe by dx. So, this is the force, this is the non-equilibrium force on the probe. So, the work done on the probe by this force is given by this expression. So, if we know the distribution in the stationary distribution in for the medium, then of course we can calculate it exactly, but that is not typically the case. So, we look for some perturbative expansion for this Gx. So, this is the linear order correction and higher order corrections. But it happens that even without knowing this distribution fully, we can say something about this G1x, which is still of thermodynamic nature. So, it is not gradient anymore, but it can still be obtained from irreversible thermodynamics. So, there is a theorem by McLennan which says that up to first order this distribution can be calculated, and this Hx is related to the excess work done on the medium. So, what do I mean by excess work? So, typically when a system is in non-equilibrium, there is a constant heat dissipation to the ambient medium. So, for a given position of the probe x, there is a constant heat production for the medium. And now when the probe position is changed from x to x plus dx, the system, by system here I mean the medium, eta medium, it starts to relax to a new stationary distribution. So, we have this maybe I should not go. So, we have a rho x, and then it relaxes to rho x plus dx, and this, if we measure this area from this work rate, so this is what I mean by excess work. So, this is a constant value in the new stationary state, and this was a constant value in the previous stationary state, and this is the excess work done on the medium by the external drive. So, what we can show is that the work done on the probe by this medium is actually equal to this excess work done on the medium by the non-equilibrium drive. So, this provides a way to measure this excess work. So, these excess quantities appear in non-equilibrium thermodynamics everywhere: excess work, excess heat, and excess entropy production. So, this gives us a mechanical way to measure this. I will skip the kinetic aspects, but in one line, so these statistical forces also provide a way to measure kinetic aspects of the medium, but yeah, there is no time. So, next important aspect is the non-additivity. So, for a medium which is in equilibrium, the force on the probe is given by the free energy, as we said, and the free energy is local and additive, which means that the force, if we consider force on the probe from two different media which are weakly interacting among themselves, these forces are additive. So, the total force on the probe is just given by force on the probe by medium 1 plus the force on the probe by medium 2. But but in non-equilibrium, usually you expect long range effects. So, even when these media are weakly interacting, one can have long range effects in the stationary distribution, and then it's it's not expected to be additive anymore. So, again let us see a very simple example. So, we have our probe, which is again on a circle for just simplicity, and now it is interacting with two different media. So, two 3-state processes, I will call these A and B, and so this coupling is still energetic with some U1 and U2, and these two media are interacting via some weak link gamma. So, we think that a particle is doing a random walk on this network with some rates which are given by the energy, and we want to see what happens to the total force on the probe. So, for the density rho A and B, so because these energies are different, there would be some density rho A and rho B, which are the probability that the particle is in part A or part B. So, the total force is given by this sum, and so we define a measure of non-additivity, which is basically the difference of this force when this coupling gamma is 0. So, when we have two completely disconnected media and when we have a weakly interacting set, and then we see that this, so this is, we again calculate the rotational component of this non-additivity, and we see that it is very non-trivial when we plot it against epsilon. But what we also see is that it increases with gamma, the magnitude increases with gamma as we expect. When the two media start to interact stronger, the non-additivity increases. And yeah, again there is a rotational component of it, which means that the non-additivity itself or the rotational component itself depends on, it is non-gradient, it cannot, it can also not be generated from any potential. So, yeah, to conclude, we basically studied statistical forces from driven medium, and it shows many different features from compared to equilibrium. So the force on any slow probe is of non-gradient nature generally, and when we consider a linear regime around equilibrium, the force is still of thermodynamic nature, in the sense that you can one can consider one can relate it with the excess work done on the medium, and then they also provide operational meaning, but this I skipped, and they are generically non-additive. And here we just consider very simple toy systems, but this formalism can be directly applied to more realistic systems of interacting particles, or yeah, and it also provides a possible way to measure certain things which are not possible in equilibrium. So thank you for your attention. Yeah. Mm-hmm. Mm-hmm. It also, yes, 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 yes. Yes, because yeah, but if they are weakly interacting, then you have a local free energy, and the free energy is additive. So in the limit of large system size, I mean large n or large number of particles, they are always additive. Yes, if the interaction is no, it's not additive even for small gamma. No. So this is small gamma, or you can also see the force on the probe as a function of x. So it's non-zero even for small gamma. Yes, when gamma goes to 0, it is 0. But yes, but in equilibrium, even in first order in gamma, it's 0. I mean, it's additive. Yes. 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 In non-equilibrium. Even in yes, I mean this is just a small system, but we saw examples even in the large limit. Yes. It could happen. Yeah, I don't know. I don't know. I mean, we didn't do any detailed calculation for large n limit, but it could happen. Yes. Yeah. Yes, yes, it is. It is similar to that. So what Capri and they found is that in some cases you can define you can define an equation of state, but in some other cases, so you have a wall, and the equation of state actually explicitly depends on the wall potential. So it is really it is more directly related to the kinetic aspects, which I did not say, but it's yeah. Yeah.
Of free energy.
Yes.
Equilibrium.
Yes.
So could you derive your force, your non-equilibrium force, as a gradient of the large deviation potential?
That is not exactly clear. We did not really try very hard, but it's not obvious. No, it's not obvious. Yeah.
You think it's true or wrong, or?
Probably not true in general.
Okay.